you, sir.
We can now proceed to our next technical session of day 6. It's my privilege to introduce our next distinguished speaker, Professor David Megías. Uh, Welcome, sir. I think you have joined. Sir, am I audible to you?
Good morning. Can you hear me?
Yes, sir. Yes, sir. You are audible. Uh, okay. So let me just give a brief introduction of our esteemed speaker today. Professor David Megías received his PhD in computer science from the Universitat Autònoma Barcelona, UAB in July 2000. He is currently a full professor and co-principal investigator of Keystone Research Group at the Ethical Technologies and Connectivity for Humanity Research Center, Universitat Oberta Catalunya, UOC. He has been associated with UOC since October 2001 and has held several key leadership roles, including Director of IN3 from April 2015 to May 2025 and Director of UOC Tech since May 2025. His teaching and research span computer networks, information security, watermarking, steganography, and research methodologies. Professor David has an impressive research record with over 150 publications, including 49 papers in index journals, and successfully supervised 6 PhD theses. He has also contributed extensively to national and international collaborative research projects. His current research interests include information security and privacy, secure multimedia content distribution, watermarking, and fingerprinting, steganography, steg analysis, and privacy challenges in decentralized network applications. We are honored to have such an eminent academician with us today. The title of the session is Securing the Smart Edge, AI in IoT Devices and Embedded Systems. With this, I warmly welcome Professor David to take over the session. Thank you, sir, for joining us. And it is our privilege to have you with us, and you can now start the session.
Thank you very much for your very nice introduction. It's my honor to have been invited to this event, and I hope you will enjoy my presentation. So I can now share my screen. Is it okay if I share my screen now?
Yes,
Yes,
sir.
sir, you are.
Please.
Thank you. I'm looking for.
Participants, the previous session feedback link is shared in the chat box. You can fill the link side by side. Sir, you can carry on.
Yeah, I think I'm trying to share my presentation. Okay. But somehow I cannot choose the. Let me try again. No, I'm having trouble to.
Sir, just you can click on share option.
Yeah,
And then
I'm trying that, but somehow I cannot choose my file for some reason. Let me try again. Okay. No, I cannot share my screen for some reason.
Okay, sir, let me ask the technical team to share
Mhm.
to share the presentation on the screen.
Hello, good evening, sir.
Good evening. Good evening. Good afternoon.
Sir, Dr. Rahul this side. Sir, just click on the share button, then
Yeah, I did. Yes.
and just select the your PPT from the Windows and your screen also. You can just share the screen also and your window also. Just try, sir, one time.
Yeah.
I have given the permission to you.
Okay. Okay. So maybe. No. So I'm trying to share the window, but I don't get the possibility to select any of my applications.
Yes, sir. Just select from the Windows. You can just share the screen or Windows. It's your
Yeah,
choice,
yeah,
sir.
yeah. I'm trying, but when I choose the window, then I don't get any dialogue to choose any
S-
any of
Sir,
my open windows.
you have just opened your PPT on a slide mode and any other mode, sir. You have just opened or not, sir, right now.
I have it open. It's open. It's
Sir,
not.
you have
It's
opened your PPT in your screen on your screen.
yes, I have it. But when I choose the option to share my screen, I change window. I choose window, but nothing happens. Okay, okay. Okay. I need to give permission to my Mac. I see.
Yes.
Okay. The permission was not granted. Okay, I see. So that's a problem with the setup of Teams. Okay, let me give it permission. Okay. Okay, possibly I'll have to rejoin.
Rahul, please unmute, Professor.
Sir, unmuting.
Hi, yes. I think I have finally solved.
Yes, sir, your PPT is visible. You can start the slideshow, sir, also.
So yeah, let me. Okay. So let me start the presentation. Sorry for the trouble, but somehow this version of Teams was not given permission to share the screen. So good morning, good afternoon for you, everyone. This is David Megías from Open
Good afternoon,
University.
sir.
Yeah. So if you want, I can start now. Is it okay?
Yes, sir, you can start. Yes, sir.
Okay, thank you. So I will give my speech on securing the smart edge with AI in IoT devices and embedded systems. Okay, this is again the first the title of the presentation, but this is with the logos of my funders. And let me now introduce the outline of my presentation. I will begin with an introduction to the topic. After that, I will briefly introduce Zircon, that is a zero watermarking based data provenance approach for IoT networks. After that, I will present the proposed hybrid solution that combines zero watermarking and machine learning using this combined IDH framework. Later on, I will go on with some experimental results, and I will finally conclude with some final remarks and some suggestions for future research directions. So let me begin with the introduction. Well, in this picture, you can see the typical layout of the IoT, edge, and cloud computing layers. So in the IoT layer, you have different sensors and actuators. Like, for example, in a smart city, you can have smart traffic systems, also connected cars. You can also have smart grids by having some devices controlling the power supply. Also, you can find IoT in e-health systems or in home scenarios like personal devices and wearables. And of course, you can also have IoT environments in manufacturing, in an industry. These typically are very limited devices with short computation capabilities and also very small memory. Then you have the edge. The edge is a collection of devices that are close to the IoT sensors and actuators, but they have typically more computational resources. And in the end, far away, you have the cloud in which you can run cloud processing, optimal routing, big data analytics, cloud storage, or business applications. So in this presentation, um, we will focus on the right side of these slides that shows the IoT access layer and the edge computing. So what's the challenge here? Well, at this moment we are having an unprecedented scale and diversity of IoT devices. We are funding billions of this kind of devices being connected to the network in different places. And this is creating a massive and continuously growing attack surface that is very difficult to monitor and protect. Also, as I already mentioned on the previous slide, these kind of devices, both in the IoT and the edge, have limited computational power, memory, and energy supply. And for this reason, trying to apply heavy security solutions like complex encryption or deep learning models is often not possible in this kind of resource constrained devices. So what's the threat landscape here? We find that the network, this kind of environment is quite vulnerable to diverse and evolving attacks. And this includes physical tampering, data breaches, DDoS attacks, or also sophisticated routing attacks. And in addition, we have another threat that is zero-day exploits. These are unknown attacks that we don't have any reference of them in the past, and these require proactive detection mechanisms that don't rely only on known signatures. So this is more or less the challenge that we want to solve. And in this kind of environment, AI and machine learning are mandatory. Uh, Before going to artificial intelligence solutions, we could try, or it has been tried actually, to deploy other kind of intrusion detection systems for the IoT and edge. One of these examples is a signature-based IDS that they rely on matching incoming traffic patterns against a database of known attack signatures. These kind of solutions are very accurate for known attacks, but they fail completely to recognize zero-day attacks. So this is not the optimal solution in this environment. Another possibility is to rely on specification-based IDS that require manual definition of all normal network rules and thresholds. But this is really quite time-consuming and also inflexible when you try to apply this solution to a new IoT environment, because the parameters typically need to be recomputed and adjusted. So the only way to detect novel and evolving cyber threats in this kind of situations is to apply anomaly-based intrusion detection. In these solutions, the the detection works by defining a baseline of normal behavior and identifying any significant deviation from that baseline as suspicious, as a potential intrusion. But of course, we need to consider that IoT generates an enormous quantity of data, and this, of course, cannot be analyzed manually. So machine learning is the solution that provides the necessary intelligence and learning capabilities to automatically learn the complex internal relationships and distinguish between normal and malicious traffic. So um, that's the typical approach in this kind of scenarios, but also we have a problem here. This problem, I will call it as the fundamental flaw of machine learning solutions. What's that? What's that problem about? Well, all machine learning models are inherently imperfect in the sense that regardless of how much effort you devote to the design of the model or to the training with a very comprehensive data sets, you can never have 100% accuracy. So this imperfection means that the model will always make some mistakes in the classification of traffic. And these mistakes
Sorry,
can fall
Professor.
into... Sorry, yes?
I think your slides are not moving.
Really? Let me...
Yes.
Can you see... Can you see the movement or not?
No.
No.
Uh,
So...
you may have the
say,
slide so.
yeah, I will try the normal mode. Can you see
Slide
it
so.
now?
Yes. These are moving now.
Okay, so I cannot use for some reason, sorry for the technical issues. I
No
cannot
problem.
use the presentation mode, but I will do it this way. Okay,
Okay.
so thank you for your interruption. So I was mentioning that machine learning models cannot provide 100% accuracy. So this means that there will be some classification errors. And these classification errors can be categorized into groups. On the one hand, we can have false positives. And false positives means that we are labeling a normal activity as it was an intrusion. And this has consequences. For example, this leads to alert fatigue in the users, and they can find, for example, potential denial of service to some legitimate users whose traffic is blocked. On the other hand, we can have false negatives. False negatives mean that some attacks, some intrusions are classified as normal traffic, But this is the catastrophic error because in this second scenario, the attack can go undetected and compromise the system. So to solve, well, here we find this fundamental flaw of using machine learning alone. We have this unsolvable problem because this limitation of machine learning cannot be removed just by improving the model or the training set. And typically, the best approach to mitigate this classification problem is to supplement the machine learning system with a non-statistical mechanism, as I will describe in my proposal. Now I want to remark why the false negative is the catastrophic situation. The problem is if you let an attack go undetected and mistakenly classify it as normal traffic, this attack will enter your system and will begin compromising your devices and possibly have very harmful consequences like losing your data or leaking your data or even causing the complete interruption of the system. So that's the thing that we want to avoid in this scenario. Okay, also we have to take into account when deploying these kind of solutions that there are, as I mentioned, resource constraints at the edge. This means on the one side that we have hardware limitations like low computation power with very small processing capabilities, and also they have quite limited storage with extremely small memory and storage capacity. This is particularly true for IoT devices, but somehow it's also true for edge devices. And this prevents using host-less databases or complex software. Also, we have some energy and operational constraints like battery dependency, because most IoT deployed sensors rely on batteries, and this means that any security solutions should focus on low energy consumption to maximize the lifespan of these kind of devices. And again, we have another problem that is latency, because in many industrial or e-health scenarios, the IoT devices are sensors or actuators in a manufacturing system, and then you cannot have long delays because this could produce harmful consequences to the manufacturing process. Okay, so let me now define a little bit more precisely what's this catastrophe about. As I mentioned, there are some harmful consequences for critical systems. These include data loss or modification that compromise the integrity of sensor readings. We can have security breaches, allowing unauthorized access to and controls over our devices. And in the worst case, we will have the system downtime, resulting in significant financial or physical risks. Okay, so what I will present in this approach is quite a challenge to the current status quo. So we propose to improve the existing AI and machine learning models to mitigate the false negative problem that is inherent to machine learning by combining machine learning with a non-statistical deterministic security layer. In particular, we will be using data hiding, but other solutions are possible. And this is specifically designed to correct this critical misclassification that I have been mentioned. Another thing to take into account is this security dilemma. We want the system to be very effective, and in order to be very, very effective, we will have to use very sophisticated intelligence-based artificial intelligence and machine learning solutions, but this cannot be deployed typically on IoT and edge devices because of the limitations of power, CPU, and memory. As I mentioned, I will explain how to introduce data hiding as a countermeasure in this kind of scenarios. Our proposal is not working on machine learning solutions alone, but fusing two different techniques to increase the trust and maintain a low overhead. So in our proposal, we will be using artificial intelligence and machine learning for speed and volume. So this will be used to filter the majority of the traffic and detect anomalies quickly. And then we will introduce a second layer using watermarking or data hiding techniques for trust and screening. So we will be supplementing the machine learning layer with a lightweight deterministic primitive that protects the integrity and provenance of the data. For achieving that, we will be using zero watermarking, or reversible watermarking is another possibility. This architecture that combines data hiding and machine learning is specifically designed to minimize the effect of the false negative classifications in the system. And what we plan is to achieve a guaranteed data integrity and to minimize the catastrophic risk on this kind of environments. So the proposed solutions is published in two different papers. One is a journal paper called Zircon, lightweight zero watermarking scheme for achieving data integrity and secure provenance in resource-constrained IoT or embedded nodes. This was published in the Journal of Information Security and Applications last year. And also we published in the International Conference on Availability, Reliability, and Security, also last year, the two-layer solution that combines machine learning with zero watermarking. So now in the next few slides, I will first describe the zero watermarking solution, and after that I will come with the combination in this hybrid approach. So now let me present this zero watermarking based approach for data provenance in IoT that we call Zircon, and that was published in the Journal of Information Security and Applications. Okay, first of all, I'd like to introduce what is the data provenance problem. The data provenance problem is in this is shown in this picture. So you can have the simplest case is on the left side of the picture, where the data is generated in a source node, goes through a series of intermediate nodes to finally reach the end node. This is the simple provenance scenario. We can also have, like in the middle of the picture, aggregate provenance, in which several sensors provide their data to an intermediate node. Those data are combined in the intermediate node, and then they go through a series of hops until the end node. Or we can have a special case provenance that is shown on the right of the slide. On the right hand side of the slide, you can see that a sensor generates two pieces of data to two different intermediate nodes, but this is later on aggregated on another intermediate node until it reaches the end node. So this is the data provenance um, problem, and there are many possible solutions in the literature to store and manage this provenance information. What the option that we have selected is to use a local database that is connected both to the gateway and to the IoT or and edge devices directly. This is the picture that you can find on the left side of the slide. But there are other solutions. Other solutions, for example, you can append the provenance information to the packet, as you can see uh, on the right side of the slide. In this way, in each hop of the path of the transmission of the traffic, there is a part of the provenance record that is appended to the packet itself. Of course, there are other solutions that, for example, you can use a cloud database instead of a local database, but this, of course, increases latency, so this is not typically a good idea. Or you can use a blockchain, either a local blockchain or a remote blockchain, but this is also having the same issue about latency. So for critical system, this solution typically will not work well. Well, here you can find different scenarios or approaches to face the data provenance problem. As I already mentioned, we have chosen the watermarking approach, and in particular, zero watermarking approach among the different possibilities. And this is for provenance encoding, and for provenance storage, we have selected a local centralized database. Then on the right side of this diagram, you have the security attacks that I will introduce later on. Okay, now I will shortly introduce the zircon model that we have proposed. In this model, we have two different scenarios. This easy one is the single hop scenario, in which the sensors can directly report their data to the gateway without having to go through intermediate nodes. In this scenario, the sensor is a very constrained resource device, and it can generate a zero watermark from extracted data features of the IP datagram. And this zero watermark is stored in a local database for each packet that is sent to the gateway. And the sensor also has to store the symmetric key to communicate with the gateway. Well, in the gateway, when the gateway gets the data, it will check the integrity and provenance by querying the provenance records that are stored in the database. And also it will have to store the symmetric keys of all the other nodes in the network. Regarding the local database, it must be tamper-proof, so it should be protected with strong authentication, and it's connected to the gateway and all the nodes of the network, and it should store the generated zero watermarks at least for some time, that enough time to for the intrusion detection to work. Okay, this is the simple scenario. In the more complex scenario, we have a path through the network between the source node and the end node, and the end node is the one that communicates with the gateway. This is a bit more complex because data provenance is not a single record, but a chain of records that is generated in every hop of the path. So in this more complex scenario, the sensor generates an initial data provenance record that is stored in the local database. And then each intermediate node will check the provenance record of each data packet it receives and generate a new record for the next transmission. So in the end, for a single packet, you will have as many records in the database as hops are between the source node and the end node. And finally, the final verification is carried out in the gateway as before. So we have provided a solution that works in both scenarios. Regarding the threat model, we have considered both passive and active attacks. For the passive attack, we of course consider the eavesdropping of data. And then as active attacks, we have considered the possibility of a reply attack, integrity attack on the data, modification attack also on the data. Provenance attacks include a provenance record drop, a provenance forging, and the provenance change tampering. Also, we have considered a packet drop attack, database authentication attacks, denial of service, and man-in-the-middle attacks. So this is the threat model that we have used for our system. And this is how the zero watermark or the provenance record is created. In the provenance record, basically, we introduce three different terms. The IP address of the source or the sending device, a timestamp, and a sequence number. And all of this is encrypted using symmetric cryptography. So for this transmission, provenance record that's like this one is created. Now the zero watermark is created with the concatenation of this provenance record and also a hash of the data itself. So in the end, the watermark is appending is constructed by appending two different parts. One is the provenance record, and another part is a small hash of the payload. And this provenance data is not appended to the packet, but stored in the local database. That's why it's called zero watermarking, because there is no actual embedding of the information into the packet, but the information is stored in the database. Okay, this is a summary of how the zero watermark is created. On the left side, you find the provenance record that is constructed with the IP address of the sender, the timestamp, and the sequence number. All of this is just 12 bytes. Then this is encrypted with AES encryption, symmetric encryption. So since we are using a key length of 128 bits, this means that the size of this part of the zero watermark is 16 bytes. On the right side, you can find the hash of the data payload. From that hash, we select just the first 8 bytes. So the combination of the provenance record and the hash is just 24 bytes. So for each packet that is transmitted, this zero watermark of 24 bytes is created and stored in the local database. So this is the block diagram of the single hop scenario. In this block diagram, you see all the steps that I already mentioned. The source nodes creates the watermark with the concatenation of the provenance record and the hash, and stores that in the tamper-proof network database. On the right side, you have the gateway that reconstructs the watermark when it receives the packet and also recovers the record from the tamper-proof database. And if they match, then the traffic can be accepted. But if they don't match, if there is a mismatch between the recomputed watermark and the one extracted from the database, there is a problem and the packet will be discarded. And any attacker, of course, can be in the middle of the communication and try to either eavesdrop data or play active attacks. This is the single hop scenario. The multi-hop scenario is more complex because you can have attackers trying to eavesdrop data or modify data in each communication link between intermediate nodes, between the source node and the first intermediate node, or between the end node and the gateway. So we need to consider all these possible attacks positions on the network. This is also a sequence diagram that summarizes the the execution of the protocol. This is basically the same thing that I have already introduced. And what's the security of this approach? So we have made a security analysis of this solution, and this is the result that we have managed to prove by using a formal security analysis. The first thing that we have been able to prove is that any unauthorized party cannot access or obtain secret information that is generated by the source node, basically because everything goes encrypted with symmetric cryptography. Also, in the second theorem here, you can see that any attacker can't successfully deceive an intermediate node or the gateway by inserting fake data or deleting data from the data flow generated by a legitimate node that is transmitted to any intermediate node or the gateway. In a third security property, we have also proved that an attacker that is attempting to alter the provenance information will not be able to add legitimate nodes to the provenance record, and it will not be able to successfully add or remove nodes from the provenance of the data generated by legitimate nodes. Also in theorem 4, we have proved that it's impossible for an attacker, either alone or in collaboration with others, to add or authenticate nodes to the provenance of data introduced by a compromised node. Also, another security property, we have shown that any unauthorized attempt to modify data content through the transmission channels would be detected. That's basically, this is a consequence of having a hash of the data payload included in the zero watermark. In theorem 6, we show that by including a timestamp in the generation process of the watermark, any intent to replay a previously captured data packet will be discovered. So the replay attack is not possible. Then in theorem 7, we have shown that any attempt from an attacker to drop a provenance record from the database or alter the provenance will be detected at the base station during the verification of the zero watermark. Or in theorem 8, an attacker trying to deceive network devices to accept malicious datagrams as trusted in datagrams will be detected and examined by the implemented security mechanisms. This basically means that there will be further analysis, for example, with an IDS. Another security property is that the proposed scheme can successfully um, mitigate denial of service attacks, basically because it's very difficult from outside to produce correct provenance records for attacking packets. And finally, in Theorem 10, any attacker that wants to intercept the data communication between uh, IoT devices in a man-in-the-middle attacks would be detected with our systems. So this is the security we already have without introducing any kind of machine learning in the system. Machine learning is a second layer that I will introduce in the third section of this presentation. Okay, of course, we have evaluated the performance of this solution. For evaluating the performance, we have carried out simulations in MATLAB by simulating the system 100 times for each experiment and then providing the aggregate results for these 100 executions. And we have made basically two kind of simulations. One is to prove data integrity, including computational time and energy consumption, and a comparison with the state of the art, and also data provenance. In these particular um, aspects, we have focused on the transmission data size and the provenance length and also compared with state-of-the-art methods. Okay, as computational time is considered, here you have the time required for the generation of the zero watermark, comparing two different symmetric cryptography solutions, AES and DES. And of course, it's widely known that AES is much more efficient, and in fact, it can run 10 times faster than DES. So of course, we have used AES. And the same goes for watermark verification, because basically encryption and decryption, since this is a symmetric cryptography solution, takes more or less the same time. Regarding the computational time of the hash of the second part of the watermark, that is a hash of the data payload, this is quite fast. You can see that with any of the variants of the SHA hashing algorithm, the total time is in the order of milliseconds. So this is quite fast, and this is not a problem even with very constrained IoT devices. Now, this is a comparison with other methods of the state of the art, and you can see that our zircon solution is the one that is closer to the horizontal axis here. So we are delivering the least computational time, both for generation of the watermark and the verification, compared with solutions in the state of the art based on asymmetric cryptography, on reversible watermarking, and another solution also in using zero watermark. So our solution is the best one in terms of CPU time for generation and verification. And now regarding energy consumption, this situation is more or less the same, because basically energy consumption is very close related to the CPU consumption of the devices. So again, the proposed zircon approach is the one providing the least energy consumption in this situation. Now, looking at the provenance and the comparison in the state of the art with other provenance solutions that are based on message authentication codes or Bloom filters, for example, you can see again that the zircon solution is the one that produces the less overhead in terms of the size of the provenance record, both for the single hop and the multi-hop scenario. So we are already convinced that we have um, introduced a very efficient solution for the IoT and edge scenario. Okay, so this is the summary of the zero watermarking solutions. What about artificial intelligence and machine learning? That is the topic of this session. Okay, so now I will go to summarize the proposed hybrid solution that combines the zero watermarking approach as I have already described with a standard intrusion detection system using machine learning. This is the diagram of the proposed solution. Here you can see on the right that there are two blocks in this ZWIDS solution. The first block is a classification layer with machine learning. So we have used a standard machine learning solution for the analysis of of mm, um, traffic, of network traffic, and this classification layer with standard machine learning gives two different classification outcomes. The traffic is either normal or an anomaly. And for this solution, we have used a very lightweight machine learning algorithm, in particular a support vector machine that is really lightweight and can be deployed on limited devices. But as I mentioned in the beginning, in the introduction, the major problem with this kind of solutions is misclassification and in particular false negatives. Because of that, in the case of a packet or traffic that is identified as normal, we uh, pass this in principle normal traffic by a second layer, and the second layer is the zero watermarking zircon system that I have already described in the previous section. So in this second layer, what we do is to take this in principle normal packet, extract the zero watermark from the local database, extract the regenerate the zero watermark using the generation algorithm, comparing these two values, and if there is no match between the extracted watermark and the regenerated watermark, we label the packet as an anomaly. So we are refining the result that we have obtained with the standard machine learning classifier. And we have tested this, well, this is basically the algorithm I mentioned, and that extracts the watermark from the database, regenerates the watermark for each data packet, and compares with the extracted one. If they both are equal, then the packet remains as normal. Otherwise, it is labeled as an attack. We have tested this solution in with two different data sets. One is the CICI-DS 2017 data set. This is a data set consisting of nearly 3 million samples that contains both normal and attack traffic. Regarding attacks, it contains brute force attacks, FTPR and secure shell attacks, also denial of service attacks, web attacks, botnet attacks, and distributed denial of service attacks. And for our test, we have selected the distributed denial of service that is typically the most difficult to detect, and we have used 70% of the data for training and 30% of testing. This dataset has 85 features, and the number of records is quite well balanced between normal and attack packets. In particular, it has 43% of normal packets, and 57% of attacks. We have also used the NSL KDD dataset that is a preprocessed version of the KDD cap 99, and this was designed to reduce the redundancy and irrelevant features. And it's a very widely used dataset benchmark for the evaluation of intrusion detection systems. It has 4 attack categories: denial of service, probe attacks, U2R, and R2L. It has 125,000 samples for training and 22,000 for testing, and we concentrate on a binary classification, normal versus attack. In this case, the number of features is 42, and it's again balanced between normal and attacks. So more or less it has the same number of attack and normal packets. Okay, how do we evaluate the performance of the solution? Basically, we use 2 different tools to evaluate to have metrics on the performance of the solution. First, of course, we use the confusion matrix, that is basically the number of true positives, true negatives, false positives, and false negatives. You have the definition of those metrics here on the slide. True positives are attacks that are correctly detected as attacks. True negatives are normal traffic that is correctly detected as normal traffic. False negatives is when an attack is not detected as an attack and is classified as a normal packet, and false positive is when a normal packet is incorrectly classified as an attack. And we are also using the ROC curve, that is a representation of the true positive rate on the vertical axis and the false positive rate on the horizontal axis. And basically here we want the curve to be near this red dot on the top left corner. That means a high performance model, whereas the diagonal line represents basically a random guessing model. Okay, so this is the scenario we have used for testing the system. And of course, from the confusion matrix values, we have used the standard metrics like accuracy, precision, recall, F1 score, false negative rate, and false positive rate, and we have used that for assessing the system. So now let me summarize the experimental results that we have obtained with our solution. First, before going to the results, of course, we have first classified the features of the datasets and selected the features that provide the highest important scores. This is a relevant step when you apply simple machine learning models like support vector machines, because in this case, having features that don't really discriminate the classification is not a good thing, because it can negatively affect the classification accuracy. So we have first selected the most important features for every dataset. And here you have the comparison. I don't know, maybe I can increase the size of this. This is the comparison with other support vector machines in the state of the art. And you can see that basically for the NSL KDD dataset, we are getting accuracy that is higher than 98%. The false negative rate is below 1%. So this is quite a good result. And you can also see on the right that the training time is quite small, is 30 seconds, and the testing time is just 5 seconds. So this and this is the best solution compared with the other state-of-the-art based on support vector machines. Regarding the CI/CIDS dataset, the situation is even better. We have an accuracy that is almost 100%. In fact, the false positive rate is 0%, and the false negative rate is just 0.03%. That is really, really small. That is the smallest one among, well, not the smallest one among the other solutions, but of course the combined metrics is the best one compared with the with other support vector machines. And again, the training and the testing time is very small. Regarding the rock curves, we have the comparison here. On the left side, you can see that the purple line is our proposed solution that is very, very close to the optimal curve. And again, for the NSL key DD dataset, and the same goes for the CI/CIDS dataset, where this pink line on the is almost the perfect possible rock curve. And now, what about a comparison not with other support vector machines, but with any other existing solutions in the literature for using machine learning? So here we have comparison with two support vector machines, one deep learning and one long short-term memory solutions. For the CICIDS dataset. And again, you can see here that the solution we provide works better even than deep learning and than LSTM solutions with the best false negative rate below 1% and precision of 100%. So this solution is very effective and very lightweight, and it's even able to overcome the state of the art with much more sophisticated machine learning approaches. So now let me go to the final part of my presentation with some conclusions and future research directions for the future research. First, I have discussed the importance of the statistical limits because statistical artificial intelligence models on the smart edge, or in fact in any deployment, have the false negative problem. That means that some attacks are not correctly classified as attacks, and this cannot be removed only with changes in the architecture of machine learning or the training of the system, because this is inherently it's inherently impossible to achieve a 100% classification precision and accuracy. For this reason, we have complemented artificial intelligence with another kind of approach, that is zero watermarking. That is a good countermeasure and provides a non-statistical layer that guarantees data integrity and provenance without altering the data payloads. And we have tested the solution for viability in the edge scenario, and we have proved that this zero watermarking based solution is very lightweight and energy efficient and suitable for battery dependent IoT devices compared to other traditional methods like the ones that are based on asymmetric cryptography that is very computationally demanding. Also, we have tested this two-layer architecture, and we have shown that for the CICIDS dataset, we can achieve an accuracy of nearly 100%, 99.98%, a false negative rate almost negligible, much lower than 1%. We have also shown that we can combine in this high resolution artificial intelligence for speed detection of anomalies, and then data hiding is a second layer for fine tuning and refinement of the results by suppressing some or many of the false negatives that are a consequence of the machine learning classification. Okay, now for future research directions, we plan to apply decentralized intelligence using federated learning. And this is a very interesting approach for the edge and the IoT because the individual device constraints can be overcome by splitting the computational cost of the model training and testing among several edge devices, and this can reduce the latency and preserve the data locality by moving away from cloud-based solutions that are typically not applicable due to the latency. Regarding the combination with data hiding, we also plan to combine this federated learning approach with the zero watermarks that I have mentioned to guarantee the integrity and the provenance of the data that are used to train the local models. And this can provide a deterministic defense against model poisoning and will ensure that the updates of the models by training the decentralized nodes will remain untampered. Also, we plan to work towards adaptive intrusion detection and prevention system. So we plan to extend this two-layer framework into an adaptive systems that is capable of continuous learning and counter the evolving threats, including zero-day attacks. Another future direction is the large-scale edge governance, because we are now relying on a local database, and of course this is difficult to deploy for massive and high density network. This is a challenge, like smart cities or factories, because there is a lot of traffic in this kind of networks, and introducing a different record for every data packet that is transmitted through these networks is a challenge, and maybe other solutions should be investigated. And finally, we plan to standardize these kind of solutions to other IoT protocols. We have focused for the moment on normal TCP/IP traffic, but we can consider other protocols like BLE, 6LoWPAN, or wireless HART that are more typical in some situations. And the final goal is to create a unified security standard for the edge and the IoT. So this is the end of my presentation. Thank you very much for your attention. And now I will be pleased to consider your questions.
Thank you, sir. Participants, you can now ask your questions.
Hi, any questions?
Till now, no one has posted any question, and
Mm-hmm.
they are just giving. It is very a nice session and wonderful session.
Uh-huh.
One question came now. What is better in security for edge devices, federated learning or blockchain?
I would say that the blockchain is typically difficult to deploy at the edge, although there are solutions for that. And in fact, we in our research team have people that are developing more efficient solutions uh, for uh, for edge located blockchains. But the latency problem of blockchain can be very relevant. So my personal view is that federated learning is a better approach in this situation.
Okay, sir. Any other question from any other participant? One question is why is security by design more critical at the smart edge than in centralized AI systems?
Mhm. Yeah, it's more critical in this kind of devices because the mitigation and detection is much more difficult with edge devices and IoT devices because you have very low computational capabilities, very constrained memory, and limit also limitation in terms of battery. So the kind of mitigation that you can deploy is much more constrained than in centralized scenarios. In centralized scenarios, you have powerful servers, you can have GPUs, you can have very large memories and deploy complex solutions and algorithms. So in the case of IoT and Edge, you need to minimize the attack surface from the beginning to avoid having to deal with attacks with mitigation solutions.
Okay, sir. Thank you. Next question is hardware-based security mandatory for production-grade AI-enabled IoT devices?
Well, that's a good question. Uh, in the end, if you have, for example, cryptographic hardware, you can, from the design, avoid or prevent many harmful attacks from the beginning. So I won't say that this is mandatory, but of course this is a very convenient approach in this kind of scenarios. Whatever you can introduce in the hardware, you will make it much more difficult for attackers to be successful.
Okay, sir. Another question is, sir, from an academic and industry perspective, what security topics related to AI-enabled IoT edge devices should we start integrating into undergraduate curriculum today so that the students are prepared for real-world deployment?
Yeah, I completely agree that this should be introduced in the curricula because the actual trend is to find more and more and more IoT devices, also with 5G connection. So this is an increasing field and topic, and yeah, I think it should be introduced. There was another part of the question. Can you repeat that to
Um,
me?
it's like what security topics related
Yeah,
to AI-enabled IoT edge devices
yeah,
should be integrated. Yeah.
exactly, exactly. I'd say that security by design and intrusion detection and prevention are very relevant topics that should be introduced in the curriculum.
Okay, okay, sir. Right. Next question is, sir, what are the most common security failures seen in the real world AI-enabled IoT deployments?
Mhm. Yeah, I'd say that denial of service and distributed denial of service are the most typical ones, and also Yeah, the taking control of some of the devices to the exfiltration of data. These are the most typical ones.
Okay, sir. All right. So I hope all the questions from the participants are being answered. Any other thing anyone wants to ask? Okay, I think there is no other question. So we can conclude. Thank you, Professor David, for the enlightening session on securing the smart edge AI in IoT devices and embedded systems. Your deep insights into security, privacy, and AI driven protection mechanisms for IoT and embedded systems were really highly informative and greatly appreciable. We sincerely thank you, sir, for your valuable time and contribution for this faculty development program.
So thank you very much to you for your kind invitation, and I will be happy to participate in other future events. Thank you.
Okay, sir. Thank you.
Bye bye.
Okay,
Thank you,
sir.
sir.
Bye.
Sir, ma'am, feedback link.
Yes. Technical team,
Mm.
please post the feedback link in the session. Just wait. The link will be posted right now in the chat box.
Okay, ma'am. Thank you. Madam, is today's PPT is shared with us, ma'am?
Yes, yes, ma'am. The things, all the session PPTs will be shared on the Drive link.
Okay, ma'am. Thank you.
The link is posted in the chat box. You all can start filling your attendance and feedback form for session 12. Till the time we will start our next last session, technical session for today, that is session 13.
Ma'am, chart is disabled for me, ma'am. Is it only for me or for all? Kindly check, ma'am. Chart is disabled.
Other participants, please confirm for this. Is chat disabled or you are able to see?
Ma'am, chat is not visible on the
No,
laptop,
ma'am, it
and
is disabled,
please
ma'am.
share on the WhatsApp.
Chat is disabled, ma'am.
Ma'am, chat is visible, ma'am.
For some, it is visible, and I think technical team,
I
please
think
check
chat
for
is
this.
visible. You can check it.
Disabled, ma'am.
This is visible.
For some participants, they are saying it is disabled. Please check.
And the link is also posted in a chat group.
Ma'am, it is still disabled for me and in chat box has not yet. Kindly give the attendance, ma'am, at least.
Okay, let me convey to the team to post it in the WhatsApp group.
Yes, ma'am.